Let us consider a straight current-carrying conductor, XY, of infinite length. And like any current-carrying conductor, it produces a magnetic field around it. Now we introduce another straight current-carrying conductor, PQ, of infinite length above XY. This new conductor is in the external magnetic field of the conductor XY such that PQ is parallel to XY. Now, we will notice that due to the external magnetic field of the conductor XY, the conductor PQ experiences a magnetic force. This implies that there will also be a force on XY due to PQ in accordance with Newton's third law. From this, we can understand that two straight parallel current-carrying conductors placed close to each other exert force on each other because they lie in the magnetic fields produced by one another. Now let us find the force of attraction between the conductors carrying currents in the same direction. Let us first find the force exerted by conductor XY on conductor PQ. Let the currents passing through the two straight conductors XY and PQ be I1 and I2 respectively. Let the current through both the conductors be in the same direction. Let D be the distance between them. The magnitude of the magnetic field induction is constant at all the points, which are at equal distances from the conductor. Let the magnitude of magnetic induction due to current in XY at PQ be B1. The direction of the magnetic induction B1 at PQ can be found by using the right-hand rule. If we place a stretched right hand such that the thumb indicates the direction of current in XY, the direction of curl of the four fingers of the hand indicates the direction of the magnetic field due to the current in XY as shown. The magnitude of magnetic induction at any point along conductor PQ due to current in conductor XY is B1 is equal to mu naught I1 by 2 pi d. Let this be equation 1. The magnitude of the force experienced by a segment of length L of the conductor PQ due to the magnetic field produced by the conductor XY is F21 is equal to B1 I2 L sin theta, where theta is the angle between the direction of the magnetic field B1 and the current in the conductor PQ. Let this be equation 2. Here, theta is equal to 90 degrees and sin 90 is equal to 1. Therefore, the force acting on the segment of the conductor PQ of length L due to the conductor XY is equal to F21 is equal to B1 I2 L. Let this be equation 3. On substituting the value of B1 from equation 1 in equation 3, we arrive at the expression F21 is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 4. The direction of the force experienced by conductor PQ due to the magnetic field produced by the conductor XY can be found using Fleming's left-hand rule. According to Fleming's left-hand rule, stretch the three fingers, thumb, forefinger, and central finger of your left hand mutually perpendicular to each other. If the central finger represents the direction of the current and the forefinger represents the direction of the magnetic field, then the direction of the thumb represents the direction of the force acting on the current-carrying conductor. Thus, the force F21 is directed towards the conductor XY. As discussed earlier, the current-carrying conductor XY experiences the same force due to the magnetic field produced by the current I2 in the conductor PQ. This is in line with Newton's third law. The magnitude of the magnetic induction due to the current carrying conductor PQ is B2 is equal to mu naught I2 by 2 pi d. Let this be equation 5. The direction of the magnetic induction due to current I2 through PQ can be found by the right-hand rule. The magnitude of the force acting on the segment conductor XY of length L due to the magnetic field produced by the current through conductor PQ is F12 is equal to B2I1L, which is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 6. The direction of this force can be found by using Fleming's left-hand rule, and the force acting on the conductor XY is towards the conductor PQ. When you compare equations 4 and 6, you realize the two forces, F21 and F12, are equal in magnitude but act in opposite directions towards each other. Hence, if the currents in the two parallel straight current-carrying conductors are in the same direction, the two conductors attract each other. On the other hand, if the currents in the two straight parallel conducting wires are in opposite directions, then the forces exerted by the conductors on each other are equal in magnitude but repulsive in nature. Thus, they repel each other. Thus, the magnitude of the force F between two parallel conductors of infinite length L, separated by distance d, carrying current I1 and I2 respectively in them, is equal to mu naught I1 I2 by 2 pi d into L. Let this be equation 7. Therefore, the force acting per unit length of the conductor F is equal to F by L, which is equal to mu naught I1 I2 by 2 pi d. Let this be equation 8. Using this expression for force per unit length, let us now define the SI unit, ampere. Let the distance of separation between the conductors D be equal to 1 unit, which is 1 meter. Let the current through the two conductors be equal to 1 unit, which is 1 ampere. Then, the force per unit length becomes mu naught by 2 pi. On substituting the value of mu naught, which is 4 pi into 10 power minus 7, we get F equal to 2 into 10 power minus 7 Newton per meter. Thus, if two straight parallel conductors of infinite length, separated by a distance of 1 meter in vacuum, exert a force of 2 into 10 power minus 7 Newton per meter on each other, then the current passing through each conductor is said to be 1 ampere. The SI unit of charge is also defined from the unit of current. If a constant current of 1 ampere passes through the cross-section of a conductor in 1 second, then the charge passing through it is said to be 1 coulomb. Practically, it is not possible to demonstrate the force between the two current-carrying conductors we discussed, as the effects of magnetism are generally smaller than the effects of electricity. To study a similar effect of force, as between two current-carrying conductors, we replace the straight long wires with a coil of suitable dimensions and number of turns. We refer to this as Roget's spiral. Consider a soft spring with a natural frequency of oscillation equal to 1 Hz or with a natural time period of oscillation as 1 second suspended vertically from a rigid support. Take some mercury in a bowl and place it exactly below the suspended spring in such a way that the lower end of the spring is just in contact with the surface of the mercury. Take a DC current source, connect one of the terminals to the top of the spring, and the other terminal is connected to a switch. And then it is dipped in the mercury taken in the bowl, so that the circuit gets closed. When the circuit is switched on, due to a constant current passing through the adjacent turns of the spring, the coils attract each other, and the spring comes out from the mercury and the circuit is broken. As a natural action, the spring relaxes and again comes in contact with the surface of the mercury. Then the circuit gets closed and again the adjacent loops attract due to the current in the coil. The force of attraction between two adjacent loops in the coil is similar to the force of attraction between two parallel current-carrying conductors, when the direction of current through them is the same. While doing this activity, we should take care to keep the face away from the mercury vapors, because mercury vapors are poisonous.